Hi everyone. So in the part 3 of the videos for chapter 19, we're going to look at something called Gibbs free energy. Okay, so what's going on here? So the first thing, let's talk about once again about entropy. So we know heat that flows in or out of the system is going to change the entropy of the surroundings, right? Because entropy is going to change with temperature. So we're going to see for an isothermal process, we talked about this, that the delta S of the surroundings is equal to the heat of the system over temperature. Now, at constant pressure, remember that heat is also equal to our enthalpy, right? Delta H. So we end up getting, kind of this nice little equation here. But what can we really do with this? So in the universe, right, we're seeing that we have an entropy that can be broken really into two parts. We've got the system and the surroundings. And the sum is going to equal for the universe. And we know for a spontaneous process that sum of entropy for the universe is going to be greater than 0. Okay, so where does this play in? So if we look at the total entropy of the universe, right, it's going to equal system plus surroundings. So if I substitute the entropy of the surroundings, the equation delta H over T. Right, so we're seeing this chunk, all we're doing is we're substituting in by this amount. And then what we're going to do is we're going to multiply everything by negative T. So if we see that took the T out of the last part here, but then we put a negative T on both sides. Okay, what is she doing? Bear with me, go with it. You'll see this start playing out in just a second here. All I'm going to do is rearrange the equation. So all we did is we flipped these two. So we have delta H minus T delta S of the system. Now again, at this point, we're looking at everything in the system versus the surroundings. So that's making life a little bit easier to work with. Now the negative T delta S, right, this part, we're going to call this something new. So this is going to be delta G, otherwise known as Gibbs free energy. And that's how we end up with this equation here, which I unfortunately wrote over, that delta G is equal to delta H minus T delta S. Oh, no. So this Gibbs free energy is going to be a really important equation that we're going to use. What the heck is it? So Gibbs free energy is the amount of energy available to do work in a system. Why do we care about that? What we care is that this helps us understand whether a reaction is spontaneous or not, right? Will it occur on its own? So before we get into some of the real details with that, I do want to practice working with that equation. So in the last video, we looked to find the entropy, change in entropy for the combustion of propane. Now I want to look and try to figure out what our Gibbs free energy is for this reaction. So again, we have our reaction, combustion of propane, right? We've seen this equation many times before. A reminder that our equation is delta G equals delta H minus T delta S. And a reminder from our last video, in case you don't have the notes in front of you, we've already calculated out our change in entropy, delta S, to be negative 178.9 joules per mole Kelvin. So now you have information in the chart about your enthalpy, your delta H. So I'd like you to take a minute to use that to help calculate what your delta G is going to be. All right, fantastic. So let's check your work. So before we calculate delta G, we have to calculate our delta H for the reaction. So we know our delta H. Again, it's going to be products minus reactants. So for our products, we have 3 times negative 393.5 plus 4 times negative 241.8. Sorry about that. So that's our products minus our reactants. So we only have 1 mole of our propane, so it's just going to be negative 103.9 plus 0, because remember, for delta H, we're seeing that it is 0 for every pure element in its natural state. So when I do the math on this, my delta H is going to be negative 2043.8 kilojoules per mole. Perfect. Let's use that for delta G now. So delta G is equal to delta H minus T delta S. So we just calculated out our delta H, so negative 2043.8 minus temperature. Now if we look, we're trying to figure this out at standard state, right? So we're just going to say 298 degrees Kelvin times our delta S. Now here's where you need to be careful. Reminder, delta S is in joules per mole Kelvin. So I cannot just put negative 178.9. I need to convert that to kilojoules so it matches the kilojoules of our delta H here. So I'm going to write negative 0.1789. So that is definitely a sticking point. Make sure you are being extra careful on your units. So we see for this reaction is I calculate out the delta G and I get negative 1,990 kilojoules per mole. Or typically with Gibbs free energy, you do want to keep the numbers are going to make more sense to be in kilojoules versus joules. So it makes more sense to convert your delta S to kilojoules and not convert your delta H into joules. Okay, what the heck does that mean? So here's the big thing with Gibbs free energy. The sign of your delta G will help determine what is going on in the reaction. So if delta G is negative, we're going to see that the forward reaction is going to be spontaneous. If it's positive, it's going to be spontaneous in the reverse direction. And here's the awesome thing, if delta G is 0, the system's actually at equilibrium. So what we're going to see a little bit later on is, hey, all this is going to tie into all of the equilibrium stuff we've been working on for the last couple months. So all of this is coming together right at the end of the unit, which is so much fun. Now let's look at this in terms of signs of delta H and delta S. So we know delta H and delta S can both be positive and negative. So how is it that we can go and try to figure out what is happening just by looking at the sign? So let's take a look at an exothermic reaction, right, where our delta H is going to be negative. And let's look at something where we are increasing the entropy of the system. It is getting more random, so our delta S is positive. If we do this, right, we are taking a negative number, subtracting a positive number, and that is going to give us a negative delta G. So when we have a negative delta G, we know that process is spontaneous. So as a result, everything in the quadrant with a negative delta H and a positive delta S is going to be spontaneous. Now let's take a look at the reverse. So let's say I have a positive delta H and a negative delta S. I'm going to make these black as well to not confuse about spontaneous and not spontaneous. So if my delta H is positive, I am taking a positive number and I am subtracting a negative number, right? Which is the same thing as adding a positive. So positive plus positive is going to give me a positive delta G. So I know if my delta H is positive, but so it's going to be endothermic with a decrease in entropy, the reaction is going to be non-spontaneous. But what happens now if our signs are going to be the same? So let's say both are going to be positive. Right, I have a delta H and I'm subtracting another positive number. Now that could result in both a positive or a negative number. And what's that going to depend on? it's going to depend on the size of our temperature. How big is our temperature going to be? So what we're going to see is that part of the values are going to give us a non-spontaneous reaction, while part are going to give us a spontaneous reaction. And if you work through the math, what you'll see is at high temperatures, it's going to be spontaneous because you're subtracting a bigger number. But at low temperatures, you're going to end up with a value of delta G that's going to be positive, which means it's going to be not spontaneous. Now, if I look at the very last quadrant, if I flip all of this, so both of these values are going to be negative, right? We're going to see very similar trends, but just in opposite ways, because I have a negative number that I'm subtracting a negative from. So I'm taking a negative number and adding to it another value. So in this case, if my temperature is low, I'm not going to be adding enough to kind of undo the negative total of the value. So my delta G will be negative, which will make it spontaneous. But if my values of temperature are going to be high, right, if it's going to be a hot reaction, then we're going to see it be non-spontaneous. So again, if your signs are the same for delta H and delta S, it's going to depend on temperature. But if your delta H and your delta S have opposite signs, then the answer is going to be definitive as to whether or not your reaction is going to be spontaneous or not spontaneous. So to take a look back at the reaction we looked at for propane, right, our delta G here, it's happening at a temperature, right, because both our values are negative, but it's happening at a temperature where we're getting a negative delta G, which means this is going to be a spontaneous reaction. So again, this table here, if you end up wanting to screenshot this, this summarizes a lot of what we just talked about in terms of spontaneity versus temperature. So just keeping in mind what the temperature is, what the signs are, all of that's going to help dictate what's happening with that free energy. So another way we can look at free energy is in the same way we've been looking at everything else, right? We can look at it with respect to products minus reactants because all of our compounds are also going to have a standard value of free energy. If you go back in your book, take a look at that Appendix C, which I know we've referenced many times already, you will notice not just the delta H, which we looked at, previously first semester, you're going to see your delta G and S values as well. So we can look through all of these Gibbs energies. And again, notice Gibbs isn't going to be in kilojoules per mole, just like your delta H. And also, just like our delta H, any elements in their natural form are going to have a delta G equal to 0 as well. So what we're going to do is we're going to take a look at this reaction one final time to figure out delta G for the combustion of propane. I'm going to do a quick equation right here. Right, we've seen this before, C3H8. All these are in the gas phase. I'm not going to write that for the sake of time. It's 5O2 yields 3CO2 plus 4 waters. Right, and then just using the delta G table, I want you to take a moment and calculate the Gibbs free energy of this reaction. All right, let's take a look. So again, products minus reactants. So for CO2, I have 3 times negative 394.4 plus, excuse me, for water, 4 times negative 228.57. So that's going to be our products minus our reactants. We're looking at negative 23.47 plus, again, oxygen's gas in its standard state. So it's just going to have a delta G of 0. So when all is said and done, when I calculate it this way, my delta G is going to be equal to negative 2,074.01. A little bit different than what we calculated before. Okay. Taking a little bit of variation is going to happen. All right, I really appreciate you listening to this. We will do a lot more practice in class. Let me know what questions you have. Thanks.